You'll find out what buffer solutions are and how they are prepared. A buffer solution can be defined as a solution that minimizes changes in pH when small amounts of acid or base are added to it. Or it can also be defined as a solution that maintains a relatively constant pH when small amounts of acid or base are added to it. To get an idea of what a buffer solution does, we'll start with 1 liter of pure water. Water is unbuffered and it has an initial pH of 7. Now we'll add 0.1 mole of strong acid HCl to the water. Watch the pH meter. We'll note here that the final pH is 1. The pH went from 7 all the way down to 1, so we can see that it has decreased by 6 whole units. Now we'll go back again and start with 1 liter of pure water. Again, its neutral pH is 7, and remember, water is unbuffered. This time, we'll add 0.1 mole of the strong base NaOH. Watch the pH meter. We'll make a note here that the final pH is 13. The pH went from 7 all the way up to 13, so that's an increase of 6 whole units. What we'll do now is replace the water with a buffer solution. This particular solution contains 1 molar acetic acid and 1 molar sodium acetate. We see that the initial pH is 4.74. Now we'll add 0.1 mole of the strong acid HCl to this buffer solution and see what happens. We see that the pH has gone down, but only down to 4.66. In going from 4.74 down to 4.66, the pH has dropped only by 0.08. This is a very small change in pH. Compare this with the very large drop of 6 pH units when 0.1 mole of HCl was added to unbuffered pure water. Now we'll go back and start again with our buffer solution that has an initial pH of 4.74. This time, we'll add 0.1 mole of the strong base NaOH to 1 liter of this buffer solution and see what happens. Make a prediction. As a result of adding the base, the pH rose slightly to a final value of 4.83. The pH started at 4.74 and rose to 4.83, so that is an increase of only 0.09, which is a very small increase. Compare this with an increase of 6 whole pH units when NaOH was added to pure unbuffered water. We'll summarize our results. When a small amount of acid is added to pure unbuffered water, the pH drops dramatically. And when a small amount of base is added to pure unbuffered water, the pH rises dramatically. But when a small amount of acid is added to a buffer solution, the pH drops very slightly. And when a small amount of base is added to a buffer solution, the pH rises very slightly. So now we know what a buffer solution does. It minimizes changes in pH when a small amount of acid or base is added to it. So now what we'll do is take a look at how buffer solutions are prepared. To be able to minimize changes in pH, a buffer solution must be able to partially neutralize both acids and bases that are added to it. In order to do this, it must contain relatively high amounts of both a base and an acid. This can only occur if the base and acid are both weak. A buffer solution consists of a weak conjugate acid-base pair in which both the acid and the base have relatively high concentrations. An example is a solution that contains 1 molar ethanoic or acetic acid, which is a weak acid, and 1 molar ethanoate or acetate ion, which is a weak base. We'll use the more familiar names acetic acid and acetate ion here. In this solution, an equilibrium is established in which the concentrations of acetic acid and the acetate ion are both 1 molar, and the hydronium ion concentration is quite low. The 1 molar acetic acid is available to neutralize small amounts of strong base that might be added to this solution. And the 1 molar acetate ion is available to neutralize small amounts of strong acid that might be added to this solution. To prepare a buffer solution, molecular acids can be added directly. To prepare the buffer in this example, concentrated acetic or ethanoic acid can be diluted to 1 molar. We can use soluble ionic salts as sources of ions in a buffer solution. To make this buffer, we could add 1 mole of solid sodium acetate or sodium ethanoate to enough 1 molar acetic acid to make 1 liter of solution. The salt sodium acetate dissociates into sodium and acetate ions. The ion in the salt that's not part of the buffer solution is a spectator ion. In this case, it's the sodium ion. And we'll discard it, and we're left with the acetate ion, which is part of this buffer solution. This buffer is prepared using the weak acid CH3COOH and a salt of its conjugate base, NaCH3COO. Buffers prepared using a weak acid and a salt of its conjugate base are often called acidic buffers, like this one. This is true only for combinations that produce a pH below 7. Another example of a buffer solution is the weak base ammonia, NH3, and its conjugate acid, the ammonium ion, NH4+. Here's the equilibrium equation for this buffer solution. Molecular bases like NH3 can be added directly. Again, soluble ionic salts are sources we can use for ions in the buffer solutions. NH4Cl will dissociate into NH4+ and Cl- ions. In this salt, the chloride ion is not part of this buffer, so it's acting as a spectator ion and can be discarded, leaving us with the ammonium ion, which is part of this buffer solution. So this buffer is prepared using the weak base NH3 and a salt of its conjugate acid, NH4Cl. Buffers prepared with a weak base and a salt of its conjugate acid are called basic buffers. In some buffer solutions, both the weak acid and the weak base are ions. An example is the solution containing 1 molar dihydrogen phosphate, H2PO4-, and 1 molar monohydrogen phosphate, HPO4-2-. Here is the equilibrium equation for this buffer. The dihydrogen phosphate ion is the weak acid, and its conjugate base, the monohydrogen phosphate ion, is the weak base. Any soluble ionic compound which contains the dihydrogen phosphate ion would be a good source of this ion. An example is the soluble salt potassium dihydrogen phosphate. It dissociates into K+ and H2PO4- ions. K+ is a spectator ion, so it doesn't appear in the overall reaction, and we're left with H2PO4-. Any soluble ionic compound which contains the monohydrogen phosphate ion would be a good source of this ion. An example is the soluble salt potassium monohydrogen phosphate, K2HPO4. K2HPO4 dissociates into 2 K+ ions and 1 monohydrogen phosphate ion, HPO4-2-. K+ is a spectator and can be discarded, leaving us with monohydrogen phosphate ion, HPO4-2-. It is important for you to know that strong acids and their conjugate bases, or strong bases and their conjugate acids, are not used to prepare buffer solutions. Let's say we have a solution made by mixing solid NaCl with HCl, in which they both have a resulting concentration of 1 molar. Our solution would initially contain 1 molar HCl and 1 molar Cl-. Because HCl is a strong acid, it will ionize 100%. When ionization is complete, there is no HCl left, and the concentrations of chloride and hydronium ions have increased. Hydronium ions are available to neutralize any added bases, but the chloride ion is a neutral spectator, so it is unable to neutralize any added acids. The single arrow pointing to the right indicates that this reaction will only move forward. The reverse reaction cannot occur. Cl- ions do not react with H3O+ ions. A buffer solution has to be able to neutralize both acids and bases. What we have remaining after 100% ionization can neutralize bases but not acids. Therefore, it will not function as a buffer solution. Now let's consider strong bases. NaOH is an example of a strong base. It dissociates to form Na+ ions and OH- ions. OH- is considered to be a strong base. A strong base is able to neutralize added acids. The conjugate acid of OH- is just water, so there is no such thing as the salt of the conjugate acid of a strong base. Strong bases are hydroxides of group 1 or alkali metals, and group 2 are alkaline earths. The cation of a strong base will always be a neutral spectator ion. In this case, it's the Na+ ion. Since they are spectators, cations of strong bases are not able to neutralize any added bases. The single arrow pointing to the right indicates that this reaction will only move forward. The reverse reaction cannot occur. Na+ ions do not react with OH- ions. A buffer solution has to be able to neutralize both acids and bases. What we have remaining after dissociation can neutralize acids but not bases. Therefore, it will not function as a buffer solution. Just a couple more things about buffer solutions. In order to be an effective buffer solution, a solution must contain both a weak acid and a weak base. The concentration of weak acid and the concentration of weak base should be relatively high. For example, a solution with 1 molar HF and 1 molar NaF has a high capacity to buffer or partially neutralize any acid or base. A solution containing 0.1 molar HF and 0.1 molar NaF has a medium capacity to buffer added acids and bases. But a solution with 0.001 molar HF and 0.001 molar NaF has a very low capacity to buffer. There is very little weak acid available to neutralize added bases, and very little weak base available to neutralize added acids. One more requirement: as well as containing both a weak acid and a weak base, the concentration of weak acid and the concentration of weak base should either be equal or close to each other in value. For example, a solution in which the concentration of HNO2 is 0.8 molar and the concentration of NaNO2 is 1 molar is an effective buffer because these values are close to each other. But a solution in which the concentration of HNO2 is 0.8 molar and the concentration of NaNO2 is 0.002 molar is not an effective buffer. The values 0.8 molar and 0.002 molar are too different. There is enough HNO2 available to partially neutralize added strong bases, but not much NO2- available to partially neutralize added strong acids.